Well, hello and welcome back to Engineering 212 Dynamics, and I wanted to go over this second examination. Again, if you haven't looked at this on your own, I really encourage you to print out the exam without the solutions. You'll find it on the website. If you've got to this video without coming through the website, I'll post the location of the website up in the description of this video. But anyway, go to the website. Print out the sample exam. You can print it with or without the solutions. I'd highly recommend you print it out without the solutions and see if you can tackle it in about an hour. That'd be a good indication of your understanding. Once you've done that, once you've looked at the solutions, then watching this video might be a really good use of your time to look at things from maybe a slightly different perspective and whatnot. So with that warning, I'll go ahead and get started here. We'll look at the first problem. Questions 1, 2, and 3 come from the first problem. We're told we have a 8-inch diameter crank pulley. This might be like a serpentine belt arrangement on the front of an engine or something like that. So an 8-inch diameter crank pulley is rotating counterclockwise, so we've got it going that way at 2,500 RPMs. And drives the belt pulley shown. Assume no belt slip or stretch. Question number 1. What's the rotational velocity of pulley B? So we're looking for omega there, aren't we? If it has a radius of 1.5 inches. So 1.5 inches. And that's radius. So I have to be very careful comparing radius and diameter. This is the symbol for diameter. So if I go through that, I could say that, let's see, if we have a large pulley driving a small pulley, it's going to speed it up. So I'm going to take that 2,500. Remember, I think in lecture we saw that if we had a small driving a large, so this was in and this is out, that slowed it down. So the speed, omega, dropped and the torque would increase, whereas if we have a large driving a small, so we'll put the input on this and the output here, omega is going to increase and the torque will drop. So anytime that we have a small driving a large, slows it down. A large driving a small, like we have here, that's the arrangement that we have here, we're going to expect it to speed up. And what's it going to speed up? Well, by the ratio of the diameters, or the ratio of the circumference, or the ratio of the radiuses, or we saw in lab the tooth count on the transmission. So those are all functions of the diameter or the radius. So let's look at that. We've got an 8-inch diameter there. I would say that we have 8 divided by 1.5 radius. Remember, your 1.5 radius is equal to a 3-inch diameter. So we'll put that 3-inch diameter right there. And we come up with 6,667 RPMs. Now, as this goes around here, this belt is going to be going that direction, so this will be rotating that way, so it would be counterclockwise. So let's see, do we have that here? 6,000, yeah, to 3 significant figures. I think I would take that as the answer. Well, what's the rotational velocity of pulley number C if it has a diameter of 5 inches? So 5-inch diameter. So again, we are still driving from a larger 8-inch to a smaller 5-inch, so it's going to speed it up, but by just not as much. 2,500 times 8 over 5. Those are both diameters. So I can say that I have, what, 4,000 RPMs. And if we look at the direction here, this is going this way, so that will be that way, so it'll be clockwise, won't it? So I have 4,000 RPMs clockwise. Answer B. Okay, so answer C and answer B. And then the third question, put this on page number 2. The third question, what's the magnitude of the linear velocity of point D on the belt? So there's point D on the belt. It's going to have some linear velocity like that, which if we don't have slip should be the same as the tangential velocity on this pulley. I mean, if we look at the tangential velocity on that pulley, that should be the same as the velocity of point D, shouldn't it? So how can we get at that? We could say that we have 2,500 revolutions per minute times what? 2 pi radians per revolution times, what was the radius on this pulley here? It has a diameter of 8. 8-inch diameter gives a radius equal to 4 inches, right? So I'll take that 4 inches there. When I get done with this, I get to cancel this with that. I'm going to have inches per minute because the radians slip away. And I would come up with 62,832 inches per minute. Now let's see, I got feet per second over here, don't I? So before I go and hit number E, I'd probably better explore feet per second. So if I divide this by 12, I'm going to get feet per minute. And if I divide by 60, that would give me feet per second, wouldn't it? When I get done with that, divide this number here, 62,000 by 12, divide it by 60, and you should come up with 87.3 feet per second right there. Answer C. So E would not have been a good choice because we still had a units concern yet. Okay, so that's the velocity of that belt right there, which may or may not be a big deal for a system like this, but if you're designing a conveyor belt or something, could be of tremendous importance with really similar geometry. So we've got that at hand. So we'll move on. Question number 3. Not question number 3, we just did 3, didn't we? Yeah, so we're going on to question number 4, page number 3. There's a 3. And we're going to use this for 4, 5, and 6. We've got a 1 ounce projectile. 1 ounce, that's kind of weird. That's what, a 1/16 of a pound, is that right? I guess they tell us that there. We should probably know that, but they tell us that there. It's moving at 500 feet per second. Zipping along. Collides and is embedded, so it collides and embedded, so when that happens we know we have a non-elastic collision, okay, completely non-elastic, in the 3-pound block on the smooth surface, so mu is about equal to 0, right? That's what smooth surface said. We got to read these for all they're worth. Okay, we can't just read it word for word. We have to think about this and read it for all it's worth. The block is then arrested by the spring here. So the spring has a constant K equal to 5 pounds per inch. So it looks like we have something a little bit similar to the ballistic pendulum. We could use this for really the same purposes. We're firing a projectile at this. It embeds in this. This then slides over. And instead of increasing its potential energy like the ballistic pendulum, it increases the energy, what's stored in that spring there. Now, the one thing that we do not want to do is we do not want to go from kinetic energy here to spring energy. Someone might say, and trying to make it simple, but we don't want to make it more simple than it is. There's always some merit in trying to make it simple, but going from kinetic energy here to spring energy here. Well, the reason that you can't do that is because most of our energy is not conserved in this inelastic collision. If it was completely elastic, that might be a different story. So we're going to have to do on this one, just like we did on the ballistic pendulum, from here to here, we're going to have to use conservation of momentum. And then from here to here, we could go ahead and use our conservation of energy. Okay, does that make sense? Across the collision, we're going to use conservation of momentum, and then as the block collides with the spring, we'll use conservation of energy. So conservation of momentum, and then conservation of energy. So what is the velocity of the projectile on target block combination just after the collision? If the collision is inelastic, we already knew that, didn't we? So this is going from, if I said that this was 1, and this is 2, and then this is 3, we're going from 1 to 2, aren't we, here? Okay, so we're going to say that M1 V1 is equal to M2 V2. We have conservation of momentum. So if I look at M1, this block is resting, so I could say that there's no momentum here. The only momentum I have is in the projectile. So M1 V1 would simply be equal to, what, a 1/16 of a pound, and then I'm going to have to divide that by 32.2 feet per second squared. So I have to be real careful with my units, get that ounces turned to pound. That would be the mass. How fast is that going? 500 feet per second. And when you hammer this out, we get 0.9705 pound seconds. Okay. So that would be at 1. And then what do we need to do? At 2, I've got the this thing embedded in here. So I could say at 2, what do I have? I've got the mass, which is going to be 3 plus a 16th. We have the block at 3 and the projectile at 16, divided by 32.2. That would be your mass term. And then I have to multiply it by the velocity at 2. Well, I can set this equal to what? I know that this is equal to this thing, 0.9705, right there, because of this conservation of momentum. And when I solve for V2, I can say that that's equal to 10.2 feet per second. So I now know that this block is zipping along at 10.2 feet per second. 10.2 feet per second to the right. So answer C. Then what's the maximum compression of the spring? Well, again, that's going from 2 to 3, isn't it? I'm going from 2 to 3. And how am I going to do that? I'm going to use conservation of energy. I'm going to have my kinetic energy going to my spring energy. Okay, so we wrap our mind around that. Maybe we'll hop down here and look at 6. What is the system's initial momentum before the collision? Let's see. Well, we said this block was at rest. The spring wasn't moving around. So the only thing that we had was the momentum of the projectile, right? Yeah. So we had no momentum in the block, we had no momentum in the spring, so we only had the momentum of the projectile, so this is the answer right there. Okay, and this comes up in multiple choice questions. You try and put some questions in that so that you can spread the points out and not necessarily have to have a new problem for each question. So it shouldn't surprise us. We just go back, pick up this answer here. I think 3 significant figures. We would have answer B, wouldn't we? Okay, so that's nice. We can gain some momentum as we take this test. Not necessarily related to the momentum here, but Let's see, go back to 5. Kinetic energy, potential energy in the spring, right? So I have 1/2 m v squared, that's my kinetic energy, is equal to, we're going to assume that that's a linear spring. So I have 1/2 kx squared. So I need to solve, I'm looking for the compression of the spring. I solve this for x. I could say then that x is equal to what? Multiply both sides by 2. I then have the square root of mv squared divided by k, right? So what's that look like? We haven't gone off screen here. Yeah, I think I can get it on there. I'm going to have the mass. What mass are we talking about? Well, we've got the mass of this thing at 2, don't we? So that's going to be 3 plus a 16th. It's the target and the bullet embedded. And then I have to divide by 32.2. And then I have the velocity. Well, we came up with a velocity, didn't we? Right here, 10.2. And then we have to divide this whole thing by what? K. K is in pound inches, so I think I would be okay at just putting that 5 there. You can go through and check the units if you want, but the units do work out. It would turn out in feet, 0.406 feet, which I don't think we have an answer in feet. We're going to have to multiply that by what? 12, and if we multiply by 12, we come up with 4.88 inches. So we would have answer B with that. So again, conservation of momentum here, conservation of energy there. Let me double check my work here. 10.2. To get the units to work out and the math to work out, that would need to be squared, wouldn't it? Because I have the velocity squared there. So mass, that's the mass, the velocity squared, and then I have the stiffness, and that's all under the radical there. Run out of room just a little bit. So again, probably it's a little hard to see the print on this, but and sometimes my work here with the Sharpie is a little sloppy. But if you go to the website, I've also posted a solution of this where I've maybe done things slightly differently, but also it's probably a little easier to see. So again, that website, the description will be, or the website will be in the description of the video. Well, let's move on to 7. So that gives us page number 4. So we've got something that's rotating here. What are they telling us? A small 10 kilogram. So we're given mass here. The last one we were given force because we had the English system. Here, a little more common the metric system. We were given mass, 10 kilogram balls attached to a relatively light rod. What are they getting at there? That the mass of this is about 0, right? We don't have to worry about that. And that the radius is equal to 1.5 meters, about 4 feet. And the system can rotate around this vertical axis, so it's rotating about that. If the magnitude of the velocity v, right there, is 2 meters per second, what's the system's momentum? Well, remember that this is a rotational problem, and we really look at the moment of the linear momentum. I want to take the moment of the linear momentum. So I want to take the mass times the velocity. There's my linear momentum. And if I multiply that, or if we were in the vector sense, we would be crossing, but with r, and we'd have to be careful of the order there. But since I'm looking at the scalar here, I can just multiply it by r. So let's see how that works out for this. I've got the mass, which is 10 kilograms, times 2 meters per second. Isn't that what we had there for the velocity? Yep, 2 meters per second. And then I'm multiplying this by r, 1.5 meters. So I get 30 kilograms times what? Meters squared divided by seconds, right? Okay, kilogram meters. This would be what? If I pulled out a kilogram and a meter, kilogram meter per second squared is a newton. So I could say that this was a newton times a meter times a second, right? Is that fair enough? Yeah. If I take the kilogram meter squared per second, and I multiply by second over second. You can always multiply by 1, right? I've just multiplied by an odd-looking 1. So now I have a kilogram times a meter over a second squared. So that would be a newton, wouldn't it? And then I have this second remaining up in the numerator. And I still have a meter up there because I only used one of those meters. So kilogram meter per second squared, that's a newton. And then I'm left with meters times second. So I've got a newton times a meter times a second. So do I have this? Looks like answer C, doesn't it? Okay. Yeah, looks like answer C. Well, if the magnitude of the velocity is 2, so that's the same, right? At t equals 0, and a moment is applied about the vertical axis, so we're given a moment there. What then is the magnitude of the ball A, that velocity at t equals 2 seconds? Okay. So this is really just that we're applying, this is impulse and momentum. We're applying an angular impulse to this thing, and it's going to change the angular momentum, isn't it? Well, I have on the solutions, I have a statement that says assume, and then and something like this is constant for the 2 seconds. And this is really a casualty of me going through this very quickly. Usually when I do the solutions on this, I work through them as fast as I can because I want to be able to do it in maybe 10 or 15 minutes. And if I can do it in that time, then it's usually a pretty good fit for fitting into the time that I give you. And I was a little hasty in my writing here. Assume that the moment, of course the moment's not constant. So this should be mass. So we're assuming that it's not losing mass. We weren't told anything about the mass changing, so we're going to assume the mass is constant, not the moment is constant. This would be a mess of a problem if we're given this, and then we go ahead and try and think that it's constant. So we're going to assume that the mass is constant over that time period. Well, I think I need a little more space. Grab a blank page here. So if I go through this, I can say that I have m1 v1 times r plus the integral of what? M dt is equal to m2 v2 times r. Okay, so this is our initial angular momentum, and there's our angular impulse, and here is our final angular momentum. And we're going to assume that the mass terms are constant. We're also going to have this constant r, so this should hopefully be fairly straightforward. So this term here is just like in the previous problem. I can really say that this is just the 10 kilograms times the velocity of 2 meters per second times the radius of 1.5. And then I'm going to add to this the integral, and I'm integrating from 0 to 2 seconds, right? And then I have this function for m, 3t squared plus 5t plus 2 dt. is equal to the mass. We're going to assume that remains constant. That's what I was ill-expressed up there, times the radius, 1.5. And what are we looking for? We're looking for the velocity. So we'll have velocity too. I mean, after all, that's the unknown in this thing. So if I go through this, I can say that this is 30, just like in the previous problem, plus we're going to have what? T cubed over 3, so that would be just t cubed. 3t cubed over 3 would be t cubed, plus 5t squared over 2, plus 2t. I wanted to differentiate there for a second, but I need to integrate. So 0 to 2. Did I do that integration right? Let me double check that. I think we're good there. Yeah, good. Is equal to, let's see, 1.5. 10 times 1.5 would be 15 V2. So this turns out to be 30 plus 8 plus 10 plus 4, the lower limit, I don't have to worry about that because it's 0, is equal to 15 V2. So V2 turns out to be 3.47 meters per second. Okay, let me grab my calculator and just double check that math real quick. 3.47. Yeah, very good. Okay, so it looks like we needed to select 3.47. Looks like answer C there. Okay, so answer C. Well, good. Well, if we move on, then I believe that we were working on question number 8, so now we've got 9 and 10. And a lot of times we'll have a test with a problem that's described without a picture, and probably one of the first things we want to do on that is draw a picture. Oftentimes when you know you're really talking to an engineer, when you start describing a situation, they grab a little piece of scratch paper or something and they start sketching out what you're describing. So let's make sure that we can do this. A 2 megagram vehicle is driven up a 7-degree slope. Okay, so we've got this vehicle here, and it's being driven up a 7-degree slope with a constant velocity of what, 100 kilometers per hour. So it looks like we're in Canada, eh? So 100 kilometers per hour. Neglect the air drag and rolling resistance. That's good. It would be a very difficult problem taking into account the air drag. So what I think I'll do is turn this into a Freebody diagram. We're not trying to sort out front axle reaction or rear axle reaction. So I think I'm just going to go with a very simple Freebody diagram, as if we had this block like this. And we would have some normal force here. That's the road pushing back on the car. We have the tractive force here, what's trying to propel the car up the slope. We have the weight acting to the center of the earth. And the acceleration here, what's that acceleration? It's going to be equal to 0 because the velocity is equal to a constant. Okay, so that's important to recognize. I'm also going to rotate my coordinate system. I'm going to go with a x up the slope and y perpendicular away from the slope. And I think if I look here, this would be theta, right? Yeah, because I have that this is also theta. Good. So I could say then, if I wanted to sum the forces in the x direction, setting that equal to mass times acceleration in the x direction. I know this is equal to 0. That comes from that. So I've got the sum of the forces in the x direction is equal to 0. That's kind of nice because that gets us back into like statics. I don't have to worry about both sides of the equation. This one's equal to 0. So be careful with that, because obviously anytime that this is 0, then it doesn't matter what we multiply the mass by, we get 0. So let's see what we got here. We'll go ahead and take positive that way, up the slope. So I could say that I have the force F minus then this component of the weight in there, right? Minus mg times the sine of theta, because isn't W equal to mg? I believe it is. So minus mg times the sine of theta, and we know that's equal to 0. So then I could say that F is equal to, moving this to the other side, I have mg, which is going to be equal to, what do we have, 2 megagrams. 2 megagrams is equal to 2,000 kilograms, isn't it? So I have 2,000 times 9.81. So there's the mass in kilograms, the acceleration of gravity, the sine then of 7 degrees. So this turns out to be 2,391 newtons. What's required tractive force parallel to the slope? 2,391. 3 significant figures, what we usually use in engineering. So I mean, it would not be a good call to try and argue that it's E, because we got 2,391. The 3 significant figures, I think the appropriate answer would be B. Okay. If you look at the solutions that I did in class, I also, as an aside, I did the sum of the forces in the y direction. You didn't necessarily need that, but that would allow you to find the normal force if you're interested in that, or you had a different type of a problem. So then to finish up, if the vehicle's efficiency is 65%, depending on where we're talking about in the vehicle or whatnot, maybe that's a good number or not a good number, but we'll just take that, 65%. What is the horsepower developed by the vehicle's engine? Okay, well, we know that power is equal to force times velocity, right? So we could say that, let's see, we don't want kilometers, do we? So I better take this 100 kilometers per hour, and I could say that 100 kilometers per hour, I could multiply that by what? 1,000. That'll give me meters. Divide by 3,600. That's 60 squared. So that'll give me turn hours into seconds, and I get 27.78 meters per second. 27.78 meters per second. So now with that, I could take that the power is going to be equal to the force, 2,391 newtons. I'll multiply that by our velocity in meters per second, 27.78 meters per second, and I come up with 66,419 newtons meters per second. Let me double check that math there. Yeah, about 66,420. Yeah, pretty close. Good. So depending on how we handle the round off here, but I think we'll probably be able to sort out these answers. So I think we're good. Now this would also be, let's see, a Newton meter. That's a joule per second, and a Newton a meter is a joule, isn't it? So this would be a watt. Okay, so we've got 66,419 watts. We know that 746 watts is equal to 1 horsepower, or sometimes horsepower is equal to 0.746 kilowatts, however you want to do that. So with that, I could take this 66,419, that is watts, and divide by 746. That's going to be, what, 746 watts per horsepower. So when I do that, I come up with 89 horsepower. Denominator over denominator becomes a numerator, and I get to cancel those two. So in a perfect world, we'd only need 89 horsepower, but we've got an inefficient system, so there's losses along the way in the transmission and the axle and slip at the tires or whatever it might be. And again, accounting for this can be rather tricky. So we'll just take that number on face value. I don't know whether it's a good number or not, but we know we're going to have to provide more power. So I mean, if we were to take this 89 and multiply it by 0.65, we would get a number smaller than 89, which doesn't make sense, because ideally we need 89, and then we'd be saying that we need less than that. Well, what I'm going to do is I'm going to take this 89 and I'm going to divide by 0.65, because it's in percent, of course. So if I do this 89 divided by 0.65, I come up with 137. 137 horsepower, which makes more sense, because if we say our minimum that ideally that's required is 89, but we have losses, then we'd have to be putting more into it, right? Okay, if there's inefficiencies. If someone says to throw a party or something, we need $89, and there's inefficiencies in that process, we'd probably have to put more money into it, right? Same thing with this horsepower. If this is the ideal number and we have inefficiencies, we're going to have to put more into it. So 137, hopefully that answer is there. Answer C. Should be good to go then. So that gets that wrapped up. Again, print out the sample test, try it on your own, work it different ways, and go through it and make sure that you're comfortable with these concepts. Well, I will leave you there, and thank you for watching, and take care till next time.